morning, class. Today is Tuesday, May 20th. It is Coronachem, day 36, period 4 for grade 12 AP and U. The homework question I gave you from yesterday was 1428, 30 and 32, I believe. We're going to do as much of it as we can before we run out of time, because it looks like YouTube is cutting off at 30 minutes. So I'll try to move fast for you. I've copied the question on the board, and you can see that there were 3 trials conducted for a reaction in which chlorine dioxide and hydroxide react to form chlorate. And the stoichiometry of the reaction is 2 to 2 forming 1. So 2 chlorine dioxides react with 2 hydroxides to form 1 chlorate, and a chloride. Chlorate and a chloride. And also water. And the rate of the formation of I don't know what they measured, it just said rate, molarities per second. But the rate law is going to be determined by what happens to the concentration of these 2 substances, which are going to decrease. So they did 3 experiments. Between trials 1 and 2, the hydroxide concentration was constant, so no effect will be attributable to changes of the hydroxide concentration. You see the hydroxide concentration is constant here, but the chlorine dioxide concentration, it is chlorine dioxide, isn't it? Yeah. The chlorine dioxide concentration goes from 0.06 to 0.02, so there's a 1/3 decrease. Or there's 1/3 as much, not a 1/3 decrease, there's 1/3 as much. The concentration is 3 times higher here than it is here. So the chlorine dioxide is 1/3 from 1 to 2, and the difference in rate is from 0.0248 to 0.00276. If you take a proportion out of that, you get 8.9855, which is pretty close to 9. It is essentially 9. So the square root of 3 is 9, which indicates that the concentration is obviously being raised to the power of 2 to have an effect, which makes it 9 times faster when you double the concentration. So it means it's second order with respect to chlorine dioxide. Between experiments 2 and 3, the chlorine dioxide concentration is constant. You see it's constant from, it's always at 0.02. But what happens is the hydroxide concentration is tripled, which also triples the rate. You see the rate goes from 0.00276 to 0.00828. This indicates the reaction is first order. Tripling the concentration triples the rate. That means it's first order with respect to that particular reagent. So the rate law is K, the rate constant, times the chlorine dioxide concentration squared, times the hydroxide ion concentration. And then they ask you to find the value of the rate constant. So we picked the first data set and we plugged in all the values. This would be the concentration of the chlorine dioxide. This is the concentration of hydroxide. That's the rate in molarities per second. And the rate constant is 230 molarity to the minus 2 per second. Those are the units of the rate constant. In part C of that same question, it asks calculate the rate when the chlorine dioxide concentration is 0.01 molar and the hydroxide ion concentration is 0.025 molar. So rate is equal to K, rate constant, times the chlorine dioxide concentration, times the hydroxide ion concentration. Now, if the chlorine dioxide concentration is equal to 0.01 molar and the hydroxide ion concentration is equal to 0.025 molar. Plug in all the values. We just figured out the value of the rate constant is 230 molarities to the -2, seconds to the -1. The concentration of chlorine dioxide is 0.01 molar, and it is second order with respect to that one, and 0.025 molar for the concentration of hydroxide ion. So the rate will come out to be 5.7407, 40741 times 10 to the -4 molarities per second. You'll notice that how we got molarities per second is this is molarity squared times molarity, so it's molarity cubed. Molarity cubed divided molarity times molarity to the -2 gives you molarity to the +1, and then this goes in the denominator, so molarity to the molarity per second, and you would then report it to 3 significant figures, so you'd get 5.74 times 10 to the -4 molarity per second. The next question we were asked to do was 30. Let me copy down the data for you. Here are 3 experiments. They had nitrogen monoxide molarity, molarity of oxygen, and the initial rate in molarities per second. And we have 0.0126, 0.0252, and 0.0252 for the nitrogen monoxide. The oxygen concentration is 0.0125, 0.0250, and 0.0125 again. Initial rates are 1.41 times 10 to the -2, 1.13 times 10 to the -1, and 5.64 times 10 to the -2. That is our data. And it asks, what is the rate law for the reaction? The usual. I wrote that experiments 2 and 3 keep the nitrogen monoxide concentration constant, so all the change in the reaction rate is attributable to changes of oxygen concentration. So we're looking at these two. The doubling of oxygen concentration from experiment 2 to 3 causes the rate to essentially double. Is 2.003 times faster, so pretty close to double, which is a doubling rate within acceptable experimental error. This means the oxygen concentration is first order with respect to rate. In experiments 1 and 3, the oxygen concentration is the same, so we've kept that the same, but now we've doubled the nitrogen monoxide from here to there. And the rate increases by a factor of 4. Yeah, it causes a quadrupling of the rate. So when you quadruple the rate after doubling the concentration, that means it's raised to the power of 2. Because 2 to the power of 2 gives you 4. And therefore it's second order with respect to nitrogen monoxide. So we can now write the rate law. The rate is equal to some constant K times the nitrogen monoxide concentration squared times the oxygen concentration. To solve for B, which is asking us for the rate constant, rate over NO concentration squared times O2 concentration is equal to K. Well, they're asking you only for the units, so we're going to have molarities per second versus molarity squared times molarity. So that actually equals molarity over seconds over 1 over molarity cubed, which gives you 1 over molarity squared seconds, or if you like, you could say molarity to the minus 2 seconds to the minus 1. Same thing. Part C, they ask you to solve the actual values by plugging in all the numbers. I'm not going to write all that out because it's going to use up a lot of time, but I'll give you the actual numbers I got and the average that resulted. So for part C, I got 3 values of the rate constant, and they came out to be, I'll truncate at 3 decimal points, 7.105, 7.117, so that way you can compare notes, 7.105, all times 10 to the 3, molarities to the minus 2 seconds to the minus 1, so the average of those 3 equals 7.109 times 10 to the 3, and we're only allowed when you write to 3 sig figs, it comes out to 7.11 times 10 to the 3 molarities to the minus 2 seconds to the minus 1 as your final answer. And then for D, they ask you to use that rate constant average with concentrations of nitrogen monoxide equal to 0.1 molar, and the oxygen concentration is equal to 0.02 molar. Well, I sure hope you guys are doing your homework, otherwise I'm just literally talking to a wall. Okay, so a rate equals K. You understand, I'm not getting any feedback here. I see people are watching it. That doesn't mean it's my students. It could be some people, strangers, saying, hey, look at this guy talking about chemistry. It'd be nice if you guys checked in. That way I would know that you're watching. So you get 7.1. Why did I put 1 on? Oh, I use the unabridged, unrounded. Whenever you do new calculations, go back to the unrounded answer. So 7.109 actually rounds down to 7.11, but I'm using the unrounded value of K here. And then 0.1 molar times 0.02 molar equals 1.4218, 52692 molarity per second, and you get 1.42 molarity per second as your final answer. And that was D, sorry. Well, it started there, ends here. And there is a part E. Reaction rate. Well, let's see what the question asks first.
1430D, it asks, what is the rate of disappearance of nitrogen monoxide when NO concentration is 0.1 and O2 is 0.
No, that was D.
What E? What is the rate of disappearance of oxygen at the concentration given in part D?
Your reaction rate is measured via the disappearance of NO in the reaction. So this is the reaction. 2 nitrogen monoxide gas plus O2 gas yields 2 nitrogen dioxide gas. So if you have a rate of 1.42 molarities per second, and the stoichiometry is 1 mole of O2 disappearing for every 2 moles of NO2 appearing, okay, that's the stoichiometry, 1 and 2, then you're going to get 0.71 molarities per second of O2, and that's your answer, as they would say in Quebec.
32. Is the same as. I'm not gonna do that one. It's gonna use up all our time. Let me see how much time
We're up to here. 15 minutes.
Yeah, we can do that. But I'd rather move on. Okay, I'll just briefly put down the answers because they're not in the book. So.
It's the same type of question. I don't want to do the same type of question 3 times, but if you practice will make you better at it. So for 32A, the rate law comes out as rate equals K times S2O8 to the minus, not to the minus 2. I think that's called thiosulfate.
Check. Peroxy disulfate.
With iodide. Okay, and the units of K come out to molarities minus 1 seconds to the minus 1. For part B, the average, K average, you're going to do the experiment you're going to do it 4 times. They give you 4 pieces of data. You find the average of all 4 of them. It comes out to 3.98148 148 times 10 to the minus 3, which rounds to, basically rounds to 4. Because you're only allowed 2 sig figs. So that's what you get. And for part C of the same problem, you could say the peroxodisulfate disappears at 1/3 the rate of iodide. And the answer for D is 2.4 times 10 to the minus 6 molarities per second.
I'm going to stop it there for today. I'm going to ask you to do some homework on temperatures and rate. Try 1455. Yeah, 1455, you can plot the data. Use the Arrhenius equation.
Okay, so when you answer 1455, you're going to set up a graph, and it's going to be 1 over T in Kelvin, of course, and ln of the rate constant. And you should get a line that looks like that, okay? And the slope of the line is equal to negative EA over R. All right, and I got an activation energy of 43.9. Don't know if that's the correct answer because I didn't really check it. But before you plot your data, make a data table. So you're going to have, on your data table, you're going to have temperature in degrees Celsius. You're going to have Kelvin temperature. You're going to have your rate constant. You're going to have your ln of your rate constant, and the last row is 1 over T. So plot all that data and then, chart all that data, and then you're gonna plot this column and this column, 1K versus 1/2. Okay, so just compile all your data before you start trying your graph. It's a great exercise in graphing, and we'll show you what I got tomorrow, and then we should be able to, we should be able to give you a mock test and then work it all out, and then give you the actual test for that as well. All right, so we'll see you tomorrow.